Okay, so let's talk a little bit about temperature as another state, right? As another variable that we can use in the equation of state. Okay. So two definitions with temperature that I want you to know: diathermic and adiabatic. So diathermic means thermally conducting, and adiabatic means thermally insulating. Okay, and I want you to get used to these terms. Okay, a diathermic container, for example, or an adiabatic container. So here I have my like super fancy, expensive Yeti mug. Is this diathermic or is this adiabatic? What do you think? It kept that water nice and cold. It's got to be adiabatic, right? It's got to be thermally insulating. It's not perfectly adiabatic. Go away, endpoint antivirus. So it's not perfectly adiabatic, and we'll talk about that as we progress through the semester. Okay? So now with thermal equilibrium, so this is kind of what I wanted to show you with mechanical equilibrium on the other side, but I think the idea of the barometer, right? I suppose we could go back for a second, right? On mechanical equilibrium, right? If I can exert more force on this, right, then the mechanical equilibrium says that this liquid level will have to go up as more force is being applied on this liquid level, right? It goes up through that way. But of course, if I remove some of that force, if I pump vacuum on this, or there's less atmospheric pressure that day due to some meteorological phenomenon, right, then the liquid level will go down. Okay, so that's the mechanical equilibrium. So our thermal equilibrium goes as the following. So suppose that I have two containers, and this is a diathermic wall. Okay, so here if I have T1 and T2, and T1 and T2 are not equal, and of course a diathermic wall separates them, then eventually T1 and T2 will become the same temperature. Okay, and so the idea is, if let's suppose it's this situation where, okay, T1 and T2, if T1 is greater than T2, then heat will flow from T1 to T2. Okay, so T1 will become a lower temperature, T2 will become a higher temperature. And of course, if it's the opposite of that, if T2 is greater than T1, let's make that a 1, then heat will flow from the hot object to the cold object. Okay, so it's not that the cold, let's think of a good way to think about this. So heat will flow from the hot object to the cold object. Okay, that's always true. And this is what gives us the zeroth law of thermodynamics. And I'll read it for you and then I'll write it down. Okay, if A is in thermal equilibrium with B, and if B is in thermal equilibrium with C, then C is in thermal equilibrium with A. Okay, so let's write that down. If A is in thermal equilibrium with B, and B is in, I'll say, thermal equilibrium with C, then of course A is in equilibrium with C. I know that looks terrible. I can't even read it. Please use the closed captions. Look at my Fall 19 notes. Listen to what I'm saying while I'm writing it. If A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. Okay, that's the zeroth law of thermodynamics. Okay, so that's the simplest way we can start. So that's kind of more or less all of the general review I'm going to do on equations of state. From here on out, we're just going to be applying these equations of state. All right?